Hi, this is the math department at Amjad High School for grade 11. This is complex numbers session 4. Objectives of this session. First, we will solve equations in C in the set of complex numbers. We will talk about square roots of a complex number. Equation in C. First degree equations in the form az plus az equal b, where a and b are two complex numbers. Examples: solve in C the following equations. A. I z minus 5 equal 2 plus 3i. First, we have to develop here. So we get iz minus 5i equal 2 plus 3i. Second step, we take the unknown, we keep the unknown in the first member, and we take the given numbers to the second member of the equation. So 2 plus 3i plus 5i, iz equal 2 plus 8i, and now z equal 2 plus 8i over I. This one is the solution of this equation, but this form is not the algebraic form. Usually we prefer to put z in the algebraic form. To do that, you have to multiply by the conjugate of the denominator, which is minus I. So we get minus 2i plus 8 over I times minus I, it's equal to 1. So finally the algebraic form of the solution is 8 minus 2i. Example B. 2z minus 2 over z plus I equal I. First, we do cross product. Before that, we have a condition here. Z plus I must be not equal to 0, so z is different than minus I. Now we do cross product. So 2z minus 2 equal iz plus I squared, so it's equal minus 1. Now we take the unknown to the first member and the given number to the second member of the equation. 2z minus iz equal minus 1 plus 2. We take z common here. 2 minus iz equal 1 and z equal 1 over 2 minus I. Let us find the algebraic form of this equation, of this solution, by multiplying by the conjugate of 2 minus I, which is 2 plus I. So we get 2 plus I over real part squared plus imaginary part squared. So it's equal 2 over 5 plus I 1 over 5. This one is the algebraic form of the solution of the root of this equation. Equation in the form az plus b z bar equals c, where a, b, and c are complex numbers. In this case, when we have z and z bar in the same equation, usually we prefer to pass to the algebraic form by putting z equal x plus iy, where x and y are real numbers. So we have to take z equal x plus iy. Examples: solve in C in the set of complex numbers the following equations. 3z minus 2z bar equal I. Let z equal x plus iy. Then 3, replace z by x plus iy minus 2z bar is equal to x minus iy equal I. Now we multiply, we do the product here, 3 expanding, 3x plus 2iy minus 2x plus 2iy equal to I, grouping the real part together and the imaginary part. So we get 3x minus 2x is equal to x plus 5iy equal I. Now we have to find x and y. If we find x and y, you can deduce the value of z, the solution of this equation. So we have the equality between two complex numbers. So real part is equal to real part, and imaginary part is equal to imaginary part. So x equal 0, 5y equal 1. So y equal 1 over 5, x equal to 0. Now z equal, we have z equal 1 over 5i. This one is the solution of this equation. Another example: iz plus 1 minus iz bar equals 3 plus 4i. We start by z equal x plus iy, the algebraic form of the complex number. Then replace z by x plus iy and z bar by x minus iy, expand, we get ix minus y plus x minus iy minus ix minus y equals 3 plus 4i. Take the real part and the imaginary part of the first member, so x minus 2y minus iy equals 3 plus 4i. Equality of two complex numbers, so real part equal real part, x minus 2y equals 3, imaginary part minus y equal 4. So y is equal minus 4, and we replace x, y by its value here in the first equation. So we get x plus 8 equals 3 and x equal minus 5. We have x and y, so we can deduce the value of z, the solution of the equation. Z equal minus 5 minus 4i. This one is the algebraic form of the solution of this equation, of this complex equation. Square root of a complex number. Definition. We call a square root of a complex number z every complex number w, every complex number w, such that w squared equal z. So the square root of a complex number is also a new complex number, verifying w squared equal z. Examples. Example 1. We have I squared and minus I squared are both equal to minus 1. So we can say I and minus I are two square roots of minus 1, and you can remark that I and minus I are two opposite complex numbers. Example 2. We have also 1 plus I squared equal to I minus 1 minus I squared equal to I. Then we say that 1 plus I and minus 1 minus I are two square roots of 2i. And you can check also 1 plus I and minus 1 minus I are two opposite complex numbers. So the square root of a complex number are two opposite complex numbers. Example 3. We have 2 plus 3i squared equal minus 5 plus 12i. You can try that on the calculator. Minus 2 minus 3i squared equal minus 5 plus 12i. Then we say that 2 plus 3i and minus 2 minus 3i are two square roots of this complex number. Remark, every complex number has two opposite square roots in C, opposite square roots, 2 plus 3i minus 2 minus 3i, and we see that on the previous examples. Application 1. Verify that w equal 1 minus 2i is a square root of z equal minus 3 minus 4i. It's enough to verify w squared equal z. It's sufficient to prove that w squared equal z. W squared equal 1 minus 2i squared. This one is in the form a minus b squared is equal a squared minus 2ab plus b squared. 1 minus 4, it's minus 3 minus 4i equal to z. So w squared equals z, then w is a square root of z. Application 2. Match each of the following complex numbers z to the left to its proper square roots, the w to the right. So we have two columns here. The numbers here are square roots of the numbers here, and we have to match them. First, we have minus 3 squared equal to 9. So 9 has as square root minus 3, or minus 3 is a square root of 9. We have 1 plus 3i squared equal minus 8 plus 6i. Let us verify that on the calculator. I will take, let me pass to the complex mode first, menu 2. 1 plus 3i square equal, check that, it's minus 8 plus 6i. So we can deduce that 1 plus 3i is a square root of minus 8 plus 6i. Now 2 minus I squared is equal 3 minus 4i. Let us verify that on the calculator also. We are already on the complex mode. We have a I here, so 2 minus I square equal 3 minus. So like we see on the calculator, 2 minus 3i square is equal to 3 minus 4i. So 2 minus I is a square root of 3 minus 4i. Now 5i squared is equal to minus 25. This is easy. So 5i is a square root of minus 25. But in order to find a square root of a complex number a plus ib, where a and b are real numbers, we follow these steps. So if we don't have the square root of a complex number and we want to find a method to calculate to find the square root, we follow these steps. First step, suppose that x plus iy is a square root of a plus ib, where x and y are real numbers. Second step, since x plus iy is a square root of a plus ib, so x plus iy squared is equal to a plus ib. Third step, we solve the system. This one, when we develop this one, we get as a real part x squared minus y squared equal to the real part here, a. The imaginary part here will be 2xy, and we put it equal to the imaginary part of the second member equal to b to calculate x and y. We get 2 square root. When we have x and y, we get 2 square roots, and we will see that on the example. Application. Find the square roots of z equals 3 plus 4i. Let x plus iy be a square root of 3 plus 4i, where x and y are real numbers. We have to find x and y. X plus iy is a square root of 3 plus 4i, so x plus iy squared is equal to 3 plus 4i. Now let us expand this bracket. So we get x squared plus 2i xy minus y squared equals 3 plus 4i. Real part equal real part, so x squared minus y squared equals 3. Imaginary part 2xy equal 4. We have to calculate x and y. First, 2xy equal 4, so y is equal to 4 over 2x is equal to 2 over x. We substitute that in the first equation. So we get x squared minus, replace y by 2 over x squared, so 4 over x squared equals 3. Making same denominator and cross product, we get x4 minus 4 equals 3x squared. Take all on the first member, x power 4 minus 3x squared minus 4 equal to 0. This one, by factorizing this bracket, this equation, we get x squared plus 1 x squared minus 4 equal to 0. X squared plus 1 equal to 0, which is impossible. Remember that x is a real number. We cannot find a real number such that x squared plus 1 equal to 0. X squared minus 4 equal to 0, so x equal 2 or x equal minus 2. We have two values of x, so we will get two complex numbers, 2 square roots of 3 plus 4i. For x equal 2, replace in y equal 2 over x, so y equal 2 over 2 equal 1. For x equal minus 2, we get y equal 2 over minus 2 equal minus 1. Finally, we have two square roots, x plus iy, so 2 plus I, and x minus iy, so minus 2 minus I. Remark that 2 plus I and minus 2 minus I are two opposite complex numbers. Now let me show you how to solve this equation by calculator if you don't want to factorize. Simply we can go to menu equation if we want to calculate to solve this equation. Polynomial and choose for fourth degree. Now the coefficient of x4 it's 1, coefficient of x cubed it's 0, of x squared minus 3, of x 0, and of the numbers are minus 4. So now x1 equal 2, x2 equal minus 2. The third one and the fourth one are complex number. We don't take it because x and y are real numbers. Quadratic equations. Quadratic equations whose discriminant is real, positive or negative, doesn't matter. Example 1. Solve in the set of complex numbers C the following equations. The following equation first: 2x squared plus 3x minus 1 equal to 0. We calculate the discriminant delta. Delta equal b squared minus 4ac, which is equal 9 plus 9 minus 4 times 2 times minus 1 is equal to 8, equal 17 positive. Discriminant is real positive. We get two real roots. X prime equal minus b minus radical delta over 2a, it's equal minus 3 minus radical 17 over 2a equal 4. And the second one is plus radical 17. Let us do that on the calculator. Very easy, you know how to do it, but let me remember that. Menu, equation, polynomial, second degree, put the coefficient 2, 3, 1, and we get 2, 3 minus 1. I must put 2, 3, and negative 1, and the roots are 3 minus radical 17 over 4 and minus 3 plus radical 17 over 4. Another example: solve and see the following equation: x squared plus x plus 3 equal to 0. Delta equal b squared minus 4ac, 1 minus 4 times 1 times 3 is equal minus 12, so minus 11 negative. In R, this equation has no real roots, but in C, we replace 11, discriminant is real negative. We write delta equal minus 11, we write at the form 11i squared. We get the two conjugate complex numbers, complex roots. X prime equal minus b minus radical delta over 2a, which is equal minus 1 minus radical delta radical 11i squared. It's I radical 11 over 2. And to write on the algebraic form, it's better to put minus half minus I radical 11 over 2. And the second one is the same, but we replace the sign here by plus, so we get this one. And we can check that these two complex numbers are conjugate. Let us do it by using calculator. Very easy. Menu, equation, polynomial, second degree, and we put the coefficient are 1, 1, 3, 1, 1, 3. So we get the solution, the roots minus 1 plus radical 11 over 2, and minus 1 minus radical 11 over 2. So if the coefficient of the equation are real numbers, we can do it by using discriminant or by using calculator. Quadratic equation whose discriminant is a complex number. Example: show that 1 plus 3i is a square root of minus 24 plus 10i. Solve and see the following equation: z squared minus 5 plus iz plus 12 equal to 0. First, we have to prove that 1 plus 5i is a square root of this one, so we put it square, 1 plus 5i squared. If we get minus 24 plus 10i, so we can deduce 1 plus 5i is a square root of this number. 1 plus a squared plus 2ab plus b squared, it's equal minus 24 plus 10i, so we prove that 1 plus 5i is a square root of this complex number. Now to solve this equation, this quadratic equation, we calculate the discriminant delta. Delta equal b squared minus 4ac minus b minus 5 plus I squared minus 4 times 1 times 12, it's equal to minus 48. The minus power 2 will be simplified. Here a plus b squared, it's equal 25 plus 10i plus I squared minus 1. So the final answer is minus 24 plus 10i. Remember that we cannot keep I on the radical. So we put minus 24 plus 10i, it's equal to 1 plus 5i squared by using first part. And now we get two roots. X equal minus b minus radical delta over 2a, 5 plus I minus radical delta, radical of 1 plus 5i squared, we get 1 plus 5i over 2. And by expanding here, we get minus 5 minus 1, it's 4. plus I minus 5I is minus 4I over 2. 4 over 2 is equal to 2 minus 2I. The second equation, the second root is x double prime equal minus b plus radical delta over 2a. We replace b by its value, radical delta, so radical of 1 plus 5i. Square, we eliminate the square with the radical over 2. And now 5 plus 1 is equal to 6. I plus 5i is equal to 6i. 6 over 2 is 3 plus 3i. And now let me try to do this, to solve this equation with calculator. You will see now we are not able to do it with calculator because the coefficients are complex. Suppose I go to menu to complex mode. Now I go to menu equation, polynomial, second degree, and now I want to put the coefficients. I fill the coefficient. Here I have a 1 for the coefficient of x is minus bracket 5 plus I. I cannot put I, so the calculator, the calculus is not able to do to solve this equation when the coefficients are complex. But we can try other method. The method is to verify that 2 minus 2i is a root of this equation and 3 plus 3i is also a root of this equation. Let me show you how. Menu 2. So we are in the complex mode. I will write this equation on the calculator. How? We don't have z. I change the variable. I take x. So I take x squared minus bracket 5 plus I. Here I can put I because I work on the complex mode, plus 12. I put calc. When I put calc, the calculator weight the value of x. I put x as 2 minus 2i. 2 minus 2i. When I put equal, I fix the value of x. When I put another equal, the calculator substitutes this value in the equation. If we get 0, so 2 minus 2i is a root of this equation. Let me put 0. Okay, because here I make a mistake. I forget to put here x. Okay, let us try it another time. Calculate equal, calculate 2 minus 2i equal, so I get 0. Let me try the other value now. 3 plus 3i. 3 plus 3i equal to fix the value of x. Another equal to calculate the value of this expression. The value of this expression is 0, so 3 plus 3i is also a root. Let us try another value. Suppose we put 1 minus I. We know that 1 minus I is not a root because this equation is a quadratic and have only these two roots, but let us try that. So we get another value not equal to 0. Other thing, find the last thing I want to show you on the calculator. We cannot make a radical square root of a complex number on the calculator. Suppose I want to calculate the square root of 1 plus I on the calculator. It's math error, so we cannot do the radical on the calculator, and we have to put it to we have to write to calculate that by using the method shown on this video. So thank you to see this video.